Yes, and we are back live. Here we go. Nice. So for those of you in the chat, as you always do, please leave me a wonderful comment. That'd be fantastic. And we can get this thing kind of moving along. Just to give you an outline of what I plan on doing today. Number one, I plan on building upon what we started last class. Last class, I introduced to you, and I know it seems like a million years ago, but I introduced to you a newer concept known as logarithms. Logarithms are a means to an end. Logarithms I am going to define for you today, even farther. Logarithms we are going to use to solve certain problems. Logarithms may or may not be needed to be performed within the calculator themselves, but I'm going to show you how we're going to be handling all of these problems, especially the problems where some fancy maneuvering in the calculator is definitely needed. So yes, for those of you that are in the chat, thank you so much for leaving these wonderful comments. And if you would, ladies and gentlemen, I'm going to need you to find two specific things. Number one, yes, I'm going to need those notebooks out and open. But number two, I am also going to ask, for those of you that are here, to find this particular worksheet, which I passed out to you last week. This worksheet says 7-2 practice. On the back, it has a CUDA software page, solving exponential equations with logarithms. I'm going to need you to find that for today. For those of you in the live chat, I had posted links to the PDF. Here we go. In the Google Classroom stream last week. I just posted the link to get to that post so that you have access to these worksheets as well. Excellent. So they are all in there. Thank you for all those wonderful comments. That's so wonderful. They warm my heart, I guess. Does anybody in here need a copy of this? Does anybody in here need a copy of this? Because I'm going to be working off of this particular worksheet today. Okay, I got extras. All right. Boom. Okay. I'm going to flip my camera over. Here we go. Flip this thing going up. Here we go. And that's what we got. All right. Today, believe it or not, we are in March. What do you think about this for a second? September, October, November, December, January, February. You are done with 60% of your school year. 60%. I think the last time I mentioned this, you guys were only done with like 20%. Yeah, that's crazy. 60%. Anyway, just wanted to throw that out there. I am entitling this Solving Exponentials by Algebra and Logarithms. Again, logarithms are a means to an end. I'm going to talk about when they're needed and when they're not needed and whatnot as we keep moving along. I'm going to try this particular problem just as an example to start, to show you a problem that can be used just by algebraic skills. A problem that you actually don't require logarithms to solve, but we'll get there. So here's the example. 3 to the 6x minus 2 power equals parentheses 1/9, close parentheses, x plus 1 power. This is number 6 off of that worksheet 7.2 that we worked on last week. So let me zoom in on that, bring that up to the top, see that a little bit better. The goal with all these problems is to solve for x, to get x by itself, to isolate x. That is the goal and desire of all of these problems. logarithms will eventually be needed in more difficult problems. But this problem does not require logarithms. And the reason being is because of that 1 over 9, you can transform it to have the same base as the 3. Now I'm going to write this, and then I'm going to give my explanation as to why this is what it is in a moment. But we have this thing floating up on the screen now. Inside of those parentheses, I want you to bring your attention to what is inside of those parentheses right now. Originally, inside the parentheses, you had the fraction 1 over 9. Now, clearly, hopefully, you can recognize the fact that 9 is 3 squared. 9 is 3 squared. We know that. We've known that for quite some time, that 9 is 3 squared. But because it is written as a fraction, 1 over 9, I cannot leave it like that and hope to have the same base. I have to transform the way that fraction looks in order to get it to be the same base of 3. So just a rationale right here, I'll just put off to the side. 1 over 9 is clearly 1 over 3 squared. We know that. But what I showed you last week is that if you are taking the reciprocal of a base, if you take the reciprocal of a base, then that exponent will turn negative. Or vice versa, if you have a negative exponent, you can take the reciprocal of the base and that exponent will turn positive. In this case, this is exactly what I did. I recognized the fact that 1 over 9 is 1 over 3 squared, took the reciprocal of that 1/3, turning that exponent negative. That is a skill that we need to know how to perform. After that, I just have to clean up the exponents a little bit. If I can clean up those exponents just a little bit, I would get something like this. Move that up a bit, zoom out. Now, something I do want you to notice throughout the course of this problem, I didn't have to do anything to the left side. I didn't have to do anything to the 3. It was already a base of 3. I didn't have to change it. There was a problem last week where I believe we had to change both bases. That can happen. But this was already a base of 3, so I just kept it the same the whole way down. Whereas on the right side, I had to change that 1/9 to be a base of 3, but then to clean up the exponent, I had to multiply the two exponents together, distributing that -2 to get what I have there. The property that we learned last week was that if the bases were the same, then I could set the exponents equal to one another. That's exactly what I'm going to do. 6x minus 2 equals -2x minus 2. That -2 thing is throwing me off. Oh, well, I guess I'll see what happens. I'm going to add 2x to both sides. I'm going to add 2 to both sides. Something strange is going on here. Something strange is going on out there, too. You know what they're working on? They're working on the water fountain. You know how you guys have the water fountains have never worked all year? Yeah. You know what they promised to do? You know the thing down by the gym? Yeah. They promised at the beginning of the year that they were going to install them throughout the school. Clearly they didn't, because they suck. Anyway, not the janitors. No, not the janitors. Usually when the janitors aren't able to do something, it's because the administration is not giving them the proper supplies. Let's just put it that way. Anyway, 6x and 2x make 8x. I get a 0 on the other side. Holy crap. Wait a minute. Divide by 8. You're telling me my answer was 0 the whole time? Yeah. Yeah, it was. It was 0 the whole time. We're going to go back to the original problem to prove that in a moment. But the answer was indeed 0 the whole time. It's really nuts. But check this out. I'm going to scroll this thing back up to the beginning of the problem. If I take that 0 and I plug that thing back into the original problem, look what I get. I plug a 0 right in here. I get 3 to the negative 2 power equals, I plug a 0 in right there, I get the fraction 1 over 9. Oh, wait, that we already know that we had to do that property in order to get this thing done, because 3 to the negative 2 power is actually 1 over 3 squared, which is 1 over 9, so it works. Oh, this is nuts. Some of these problems you can solve by simple manipulation of the bases and the exponents. That's how you can solve these problems. A manipulation of the bases and the exponents. And yes, we are going to get some practice with this, with something, an assignment that I'm going to throw at you before the end of today, or before the end of the workday, I should say. Assign it on Google Classroom. We'll get that thing done. But we'll get there. So, let me show you something that's going to be a bit more icky. Something that's going to be a little bit more icky. I'm going to take a problem from the back of that worksheet. I'm going to take a problem from that worksheet, the second one that I actually posted on Google Classroom. I'm going to take this example right here. 3, I'll use x, to the x power equals 17. 3 to the x equals 17. Now we are in trouble. Now we are in trouble. What we have here is a problem that cannot be manipulated the way we just did. 3 to some power is 17. I know what 3 squared is. 3 squared is 9. I know what 3 cubed is. 3 cubed is 27. 3 to what heck of a power is 17? Last week, I introduced to you the concept of logarithms, and I am going to expand upon that today in a little bit. I wanted to show you something with logarithms with this problem. First, I have to walk you through something, and I need you all to kind of like follow along with this walk-along part. I need you all to see what you've been doing in mathematics pretty much since 6th grade. Since 6th grade, you have been solving for x. You have been isolating x. You have been finding what x equals. Since like 6th grade, that's been the goal of math. The absolute goal of math, solve for x. Redundant. But the way that you have been doing it has been by inverse operations. I need you to recognize this. I'm going to write a few things on the board, but I'm going to erase them just as quickly. Check this out. I don't know. X plus 3 equals 5. How would I solve for x? Yeah, why subtract, though? That's the word I'm looking for. Think about that for a second. You said subtract 3, which I guarantee you, like 99% of people in this school would say subtract 3. The other 1% would just not pay attention. But they say subtract 3. And I'd say, why? And you're like, because you want to get the 3 out. No. Why subtraction? And you answered correctly, because there's addition. Addition and subtraction are inverse operations of each other. Inverse operations. They cancel each other out. How would I get x by itself? Why divide? Because it's multiplication. You would recognize the fact that it's 3 times x, and you would perform division because you know that they are inverse operations of each other. You would divide by 3, you would get the x by itself. Hold on. I think I did something like this last week. I'm going to do it again. How do I get this x by itself? I got x cubed equals 81. How do I get that x by itself? Cube root it. Because a cube root and a cubed power are inverse operations of each other. The point that I am trying to make is this. Depending on what the problem is, you have to execute the appropriate inverse operation to get the variable by itself. You have to perform the appropriate inverse operation. So what I have up here is this. 3 to the x power equals 17. This is an exponential using a logarithm is the inverse operation. What the heck is a logarithm? A logarithm is the inverse to exponentials. A logarithm will cancel an exponential out. Using a logarithm on this particular problem will cancel out the 3 and leave you with the x. I'm going to show you some things on the calculator in a moment after we do this problem to kind of get the idea that what the heck are logarithms? What is a logarithm doing? Tell me. You've always been taught whatever you do to one side, finish the statement. Yeah. You've been taught that forever. Whatever you do to one side, you have to do to the other. Watch what I'm about to do here. Look what I just did right there. Trying to get that so the glare on the so that the glare on the thing isn't there. I'll have to move it up just a tiny bit more. There we go. This is an exponential, but now using a logarithm is the inverse operation. Now I'm going to put this in red so you can see it a little bit better. But watch what the heck happens. Tell me, before, when I had x plus 3, you said subtract 3. What happens when a plus 3 and a minus 3 come into contact? Yeah. Times 3, divide by 3. They cancel out. Cubing, cube rooting. They cancel out. Logarithms. Now notice that this logarithm is set to a base of 3. And an exponential with base 3. They cancel each other out. But since they cancel each other out, what are you left with on the left side of the problem? Yeah, and that's what you wanted. You wanted to get x by itself. If you could cancel out the exponential with base 3, with a logarithm of base 3, The only thing that's left is an x. The only thing we have to now figure out is how to evaluate log base 3 of 17. That's the only thing we have to do now. I'm going to show you multiple ways of getting that thing done, depending on the calculator that you have. Depending on the calculator that you have. So first, if I were to go to my graphing calculator on my Chromebook, which a lot of you guys have, obviously, not a big deal. You don't have to break this out now. I just want to show you where it is. First of all, you can hit Math. The Math button is on the left side. If you go down to option, technically it's option A, it's called log base. And with that log base function, you can type in the appropriate numbers to where they are. Now, before I hit enter, I just want to talk about what the heck this logarithm is actually saying. When I hit enter, I'm going to get a decimal, clearly, or something. And what this logarithm is saying is, well, again, think exponentials, 3 to whatever this power is will give you 17. 3 to whatever the decimal answer that I'm going to get is equal to 17. And I'm going to prove that. Chapow, there's my answer. There's my answer. There is the actual value of the answer to this problem. I'm going to write that down on my paper. X is approximately 2.579 is what it rounds to. X is approximately 2.579. And I'll show you, boom, that's, oh, no. That's what I wrote down right there. And again, I did approximately because this thing obviously does keep going forever. Now check this out. To pound. 3 to the power 578901923, whatever. 3 to that power, it gave me something that was approximately 17. Oh, you know what? I totally mistyped the number. Let's try this again. I should have gotten something a bit closer. 3 to the power of 2.578901923. There we go. Nailed it. Heck yeah. Now that decimal does go on forever, and that is an approximation, but that is what a logarithm does. So, a few ways to calculate a logarithm. A few ways to calculate a logarithm. First of all, in a TI-84 calculator, if you hit Math, option A is something called log base. You can put in the appropriate numbers in order to calculate the log. These are for TI-84 calculators. But not everybody has a log-based function in the calculator. For everything else, and when I say everything else, I'm referring to TI-83 calculators. I'm talking about your phone calculators, because your phone calculators have a log button. They do. Seriously. I tried to convince somebody of this one year. They legit told me, they're like, Mr. Markey, look, here's my phone calculator. It doesn't have log. And I'm like, what are you talking about? Just turn it to the side. And they're like, look, I turned it to the side. It didn't work. It doesn't have log. And I said, yeah, turn off your screen lock. They turned off their screen lock, turned to the side, boom, there's log. It's there. I'll show you in my calculator in a minute. But for everything else, this is what you got to do. For everything else, this is what you got to do. If you want to calculate log base b of c, you actually have to do the following fraction, and you need to know the following fraction just as a backup. You need the following fraction as a backup. There we go. For everything else, you need this. Here's the reason why. Every log is programmed to be a certain base. Every single logarithm is programmed to be a certain base. The base that we just needed, in the calculator was log base 3. That's what we needed for our example. However, not all calculators come with that log base function. They don't. For example, I'll show you the TI-83 right here. Hold on. I'll show you the TI-83. On the TI-83, if I were to zoom in right here, I'll zoom back out in a minute to show that fraction again. But if I were to show the TI-83, if I hit that math button and then went down, there is no log base button. There's nothing there. It's not there. But you do have a dedicated log button on the calculator right here. You do. It's right there. Hey, look, logarithm, cool. Here's the problem. That button is automatically set to base 10. That button is automatically set to base 10. And you can't change it. You can't. No one can. You cannot reprogram the calculator to change that button. That button cannot be changed from base 10. By the way, as a reminder, here's how you know it's base 10. Look what's above it written in yellow. Obviously, on your calculators, I think it's like blue or whatever. Don't care. But still, it's there. It's log base 10. Check this out. If I did log of 100, I get 2. Do you know why? Log base 10 or log of 100 is equal to 2. Remember, it's base 10 of 100 is equal to 2. What is the relationship between 10, 100, and 2? What's the relationship? Yeah, 10 squared. 10 squared is 100. That's literally the relationship. That's why it does that. That is exactly why it does that. Take a wild guess. Take a wild guess. What do you think log of 1,000 would be? Take a wild guess. You can do it in your head. No one wants to be wrong. No guesses? It's 3. Do you know why? It's what you said before. In fact, because it's 1,000, 10 cubed is 1,000. That's the relationship that you have here. Now, before, I was able to calculate in this calculator right here, log base 3 of 17. I can't do that here. Instead, I have to do this. That's what I have to type in. I can't type in log base 3 of 17, so I have to use this thing called a change of base formula. And it works. I'm going to show you on my phone in a moment. There's the answer right there. 2.5789, blah, 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 blah. That's the calculation. Go back to here. Log base 3 of 17. That's the calculation. You can also type it in like this. Log of 17, close the parentheses, divided by log of 3. Clearly getting me the exact same decimal. Let me show you on my phone. Hold on, check this out. Here's my phone. I turned it to the side, I'm going to zoom out just a little bit. There's my phone right there. Come on, thing. There's the log function right there. So I could do log of 17, close the parentheses, divided by log of 3. Boom. There's that decimal right there. Your phone can do this calculation. It's not a crazy advanced calculation that no one's ever heard of. It's on your phone calculator. It's ridiculous. I told you guys about Wabbit Emu, right? No? I didn't tell you about Wabbit Emu. Check this out. Look at me. You see I'm still holding my phone? Still holding my phone, right? Check this out. Look at that. Still holding my phone. See the Samsung at the top? If you have an Android phone, you can get this for free. If you have an Apple phone, that means that you suck. Is that fair? No? Okay, cool. Apple users. Android phones can download this thing. It's called Wabbit Emu. Wabbit with a W. Wabbit Emu. And yeah, you can download this thing. The Emu stands for emulator. Anyway, back to this. How does this help us? How does this help us with certain problems? Well, let me show you. Let's say that I have a car. I purchase a car for, I'm going to keep very round numbers. Let's say for $10,000. I purchase a car for $10,000. The rate of depreciation is approximately 15% per year. Now, that rate of depreciation, obviously, it depends on the car. It depends on how much you upkeep it. It depends on a lot of different things. Where you live in the country. You guys know that cars decay more on the island than they do on the mainland? Did you know that? Yeah. Do you know why? Is it the salt water? Yeah. It eats out the bottom of the cars more faster, I should say. You know? But again, it depends on so many different things. Let's just say it's 15% per year. How long until the car reaches a value of $2,500? I purchase a car for $10,000. The rate of depreciation is approximately 15% per year. How long until the car reaches a value of $2,500? This is a big question. Now, I'm going to show you how to do this, but then we're going to go back and we're going to get some practice with logarithms. I'm going to show you how this thing works. Here's the setup. And this setup is based on stuff that we did last week. There's the setup. And I want to explain why that setup is what it is. I need to explain why that setup is what it is. First, I am using that equation, y equals a parentheses 1 minus r parentheses to the x power. I'm going to write this on the board, just so we can kind of see the comparison here. And then I'm going to erase it. This is what we wrote actually on Tuesday. We wrote this stuff down on Tuesday of last week. We practiced a bit more with it on Thursday, and here we are back one more time. A represents your initial value. R represents the rate. And since this is a depreciation, this is a rate of decay, I have to do 1 minus R. X is time. That's what they want to know. I got to solve for x. Y is the resulting value. I got to solve for x. Ultimately, a logarithm is going to be needed for this problem. Ultimately, a logarithm will be needed. At what point? I don't know. I'm not there yet. But I got to solve this problem down. And I want to walk you through it. First, I got to divide by 10,000. First, I got to divide by 10,000. Now, it seems crazy, but I worked this out where the first couple of numbers are going to work out quite nicely. But if you divided by 10,000, like we talked about, you got to divide in order to undo the multiplication. If you divide by 10,000, you get the following. It's just 0.25. Now I'm ready to solve for x. Oh, next thing that you can do, by the way, within those parentheses, you could do the following. You could just make it 1 minus 0.15 is just 0.85. But now I'm ready for the logarithm. Now here's what I want to point out to you. I'm about to take a crazy step. I am about to take a crazy step. The goal for the rest of this class period after I finish this problem is to get the practice with logarithms. We need to see how they work. We need to see how they relate to one another. We need to see how they calculate out. But logarithms are needed in this moment. There are two ways of handling it. I'm going to handle it the way we did last week, where I am going to convert this particular equation into the following. Log with a little subscript of 0.85, parentheses 0.25, equals x. I am going to put this into my calculator on the computer in a moment, so I don't have to do any type of crazy conversion. But I will show you the conversion just for the sake of argument. The base that is on the logarithm, the little subscript, is the same base that is on the exponential. Just as a side note, this is exponential form, and this is log form. I wanted to show the comparison here. What I have at the bottom of the first page is exponential form, and on the top of the next page is log form. The goal of logarithms is to solve for an exponent. The goal of logarithms is to cancel out an exponential. They are inverse operations of each other, and they allow you to get the x by itself. That's the goal. That's the desire. That's what you want. I'm going to go to my calculator on the computer to get that thing done. Let's see. Math, log base. There it is. 0.85, 0.25. That's how long it'll take. X is approximately 8.53. I'm going to prove that in a minute once I actually write this thing out on paper. 8.53 what? 8.53 what? It's a word problem. Word problems deserve units. I don't know. I guess I'll just lose the points on that one, Mr. Markey. if this were like a test or something. Interesting. What do we put? I don't know. If only there was a piece of information from last week that would potentially help me. Hey, real quick. Have you guys seen this guy walking past my classroom door? He's done it like 3 or 4 times. And every single time he walks by, he like tries to slyly glance in. He's not there now, obviously, but he walked like this direction last time. Just keep an eye out if you see him. It's freaking me out. Hey, gentlemen, the answer is years. My question is, why? How do we know? It comes down to what the problem originally told you. The problem wanted to know how long until the car reaches a value of $2,500. X is measured in the exact same time unit as your rate. X is the same time unit as your rate. So if it's 15% per year, ultimately when we solve for X down here, it is also measured in years. Okay. One big reminder of exponential form versus log form. I want you to write this down again. We wrote this down last week. I want to write it down one more time, just for the sake of reiteration. Whenever you have exponential form like that, y equals b to the x power, it is the exact same thing as this logarithm form right here. Log base b of y equals x. Again, just reiterating the fact. Logarithms allow you to get the x by itself. Logarithms allow you to isolate the exponent in these problems. How we calculate that logarithm? Well, it depends. Sometimes we have the computer, sometimes we have the calculators. It really depends on what's in front of us. I'm going to this worksheet. You need to pull out this worksheet because there are a couple of problems that I want you to try in a few minutes. I'm going to show you how I would do one of them. I want to show you how I do one of them by myself, and then I want to give you an opportunity to try them. So please make sure you have this particular worksheet ready to go. So I'm going to tell you what numbers I'm going to have you do. But the problem that I would like to do with you first, that's a good one, is actually number 11 off of that worksheet. It's this one right here. It's number 11 off of that CUDA software worksheet. In the Google Classroom stream, you will find the PDFs. I also posted the link to find those PDFs in the YouTube comment section. But I'm looking at this problem. The goal is to solve for the variable. At some point, logarithms will be needed. How do I know that? There's a variable in the exponent. First things first, I'm going to subtract 3. I'm going to subtract 3 to start this problem. That is the best way to get this thing going. 9 to the n plus 10 power equals 78. You can't touch the 9 right now by division. You can't touch the 9 by division. You can't touch the 10 by subtraction. You can't. That 10 is technically up in a set of parentheses, even though they're invisible. I can't touch it. The time for logarithms is now. This is the time to use a logarithm when you are solving for a variable in the exponent. You could do a conversion, or you can do what I'm about to do right here. Visually, this shows how we cancel out that large 9 on the left side of the problem. Visually, this also shows where the numbers would go when we actually do the logarithm calculation. That log base 9 is a single entity that cancels out. See, he just went by again. See him? Oh, yeah, I saw him before. What the heck? Who is he? Anyway, that log base 9 is a single entity that cancels out with that base of 9. They cancel each other out, leaving you with that n plus 10, which is what we needed. We wanted to get that exponent by itself. N plus 10 equals, oh gosh, how in the heck are we supposed to do this? Well, one of a few ways, and I'm going to show you. Don't worry. One of a few ways. First, you could, if you have the TI-84, which you do on your Chromebooks, you could do this. Math, log base, 978. In that exact order. You have to have the base on there. You have to have the 78 in there. And you get that decimal. I'll write that down. 1.983 is what it is approximately. That's not my final answer. That is not my final answer, but we'll deal with that in a moment. Another way of doing it, and you guys have this on your phones, you have this on TI-83 calculators. Heck, you have this on scientific calculators that you can get from for like $10 at Staples or some junk like that. You can't see it, but there it is right there. You can get these like super cheap. This is a TI-30. This is how old this thing is. Check this out. Log of 78 divided by log of 9 gets me that decimal that I needed. You can do that on these crappy scientific calculators. Log of 78 divided by log of 9. Chapow. Again, same exact decimal. Now, that's not my final answer because I still have to subtract 10 to get my final answer. I still have to subtract 10. So I would go, oh, minus 10. There it is. There's my answer. There is what I needed this whole time. N is approximately negative 8.017. You will be using these skills when it comes to a project that I will eventually assign you in this chapter. In this chapter, you are going to be researching certain things such as banks, cars, and houses. And when you research these things, you are going to be determining future values, of course, but you are also going to be determining how long it will take until a certain value is achieved. And you will have to be using logarithms. Again, that's for a little bit down the line. We're not there yet. We need to get a ton more practice with what we're doing. Here's what I want you to try. on this particular worksheet, there it is. On this particular worksheet, the CUDA software worksheet, I want you to try a couple problems. Oh, which by the way, if you really want to ruin your day, I'm not teaching you this today. I'm not going to teach you this today at all. But look down at number 10 right there. I'll focus the camera in a moment. Look down at number 10 right there and tell me what gives you nightmares. What gives you nightmares about that problem? Yeah, you know what that is? Now listen, I'm not teaching you this today, but that E, you ready? Is a number. I know. You know something crazier? It's been staring you in the face this whole time. I'll prove it to you. Check this out. You guys see what's right there? Hold on. I'll move it up to the top right there. You see that right there on your calculator? You guys have had that on the TA83 graphing calculators for a while. What is that? Pi, you know that. Yeah, it's but you know it's there, right? Yeah, you know it's been there the whole time. You ready for this? There's E. It should mess with your head. Anyway, back to this. So I'm not going to have you do that problem today, obviously. But we're going to focus on a couple other problems. What I would like you guys to try and do is actually number 7 and 9. Number 7 and 9. Number 7 should literally take you, if you've been following along with me, number 7 should take you about 30 seconds. There's the guy again, by the way. I'm a little freaked out. But anyway, number 7 should take you about 30 seconds or less, maybe. Number 9 might take you a minute or so. Well, let's see what we can do with those two problems. All right. Let's just see where this kind of takes us. Even if you don't have the ability or know-how to calculate the logarithm at the moment, that is okay. You could still get to that point where you can get that variable by itself. One way of handling number 7 is by taking log base 6 of both sides of the problem. This is not the only way to handle the problem, but is definitely one way of getting that variable by itself. If you were to take correctly, and we will get the practice with this, but if you will to take correctly the log base 6 of 99, the answer is approximately 2.565 when you round it, approximately. For number 9, and this is the important part with number 9, the first thing that you should do on number 9 is divide by 5. You have to divide by 5 to start this problem. Dividing by 5 on this problem will get you 5.2. And then we can continue with what we need to do. I'll leave this up here for a little bit because I am running a little short of time. But if you were to convert to logarithm, you would get this calculation, and then you would have to divide by 6. I will be showing you this problem again next time, just for reiteration. If you haven't left a comment in the chat, please make sure that you do so. I see you all right there. Well, so far, that is. If you haven't left a comment, do so, because I'm about to sign off on this thing. We'll see you all on Wednesday. See you guys.